We've learned to use solubility product constants in calculations, and we've used them to determine concentrations of ions, but we can also use KSP to determine if precipitation will occur at all. And so we're going to work through several different problems today to talk about whether precipitation is going to occur in a particular situation or not. All right, we're going to look at example 6.8 first. Will a precipitate form when a 0.025 molar solution of calcium bromide is mixed with an equal volume of a 0.010 molar solution of lead nitrate? Okay, so let's analyze first of all what I've got. So I've got a solution of calcium bromide, okay? And this calcium bromide is 0.025 molar. So if this is 0.025, that means this is going to be 0.025 molar. This is going to be twice that, so that means that this is going to be 0.050 molar for the bromide ions, okay? Then I have a 0.010 molar lead nitrate solution. So this is 0.010 molar lead nitrate. The lead ions will be 0.010 molar. The nitrate ions will be twice that, so that's going to be 0.020 molar. Okay. Now, what it's telling me, and you have to read these problems carefully to figure out if the volume change is going to matter or not. They're saying that an equal volume of each one of these solutions is going to be mixed together, and they want to know if lead bromide is going to precipitate or not. Well, if I have equal volumes, so I've increased the volume, that means that my concentration is actually going to be cut in half. So let's set up an ice table for this again, just so we can kind of see what's going on. So initially, my lead ion concentration is going to be 0.010 molar, and my bromide ion concentration is going to be 0.050 molar. Okay, remember it was double the 0.025. All right, what's the change that's going to happen? Well, the change that's going to happen is going to be that the concentration is actually going to be divided in half because my volume is going to double when I put the two solutions together. So therefore, what that tells me is that the equilibrium is going to be 0.005 molar here, and this is going to be 0.025 molar here, okay? Again, you've got to watch and see how they're adding the two solutions together. In this particular case, they've told you they're adding equal volumes, so that means that your concentration is going to be cut in half. Now I can look at my KSP, and I didn't really allow myself enough room, so let's bring that down a little bit further. KSP equals 6.6 times 10 to the minus 6. And I've got lead ion concentration, and I've got bromide ion concentration. I don't know for sure whether I'm at equilibrium. Not positive on that. So really what I'm trying to find out, in a lot of books, you'll see this identified as a Q. So Q equals the lead ion concentration times the bromide ion concentration. But I don't know how Q is related to KSP yet. I don't know if they're equal. So we're going to find that out to see if this is going to precipitate. Okay, so because I don't know what that constant is, because I don't know if my solution is saturated, I'm going to take the lead ion concentration, which is 0.005. And I'm going to take the bromide ion concentration, which is 0.025. And of course, that has to be squared. And then when you figure that out, you end up with 3.1 times 10 to the minus 6 is what the ion concentrations, or the product of the ion concentrations, are. Well, how does that relate to this? Well, Q is actually less than KSP. So what that tells me is, since I've not yet reached KSP, my solution isn't yet saturated, and so that means that no precipitation is going to occur in this particular situation. Okay. All right, let's look at example 6.9 because there's slightly different twist on this one. Here, a student has a 0.001 molar solution of potassium chromate. This time he's adding silver nitrate drop by drop. So if we're adding it drop by drop, if they say that, then what we can assume is that the concentration is not going to change substantially, and so we don't have to worry about that in this piece. At what concentration of silver ions will the precipitate silver chromate form? Okay, so here's example 6.9. I'm looking for silver chromate. So let's get an equation written for silver chromate. CrO4. I have that solid already. So I'm going to have 2 silver ions and a chromate ion, which is also aqueous. Alrighty. I know that the KSP is equal to 6.6. Nope, I'm looking at the wrong line. 1.1 times 10 to the minus 12. And that's equal to the silver ions squared times the chromate ions. Okay. I know that it will start to precipitate as long as this number is bigger than the KSP. Okay. If they're equal, then it's saturated, but nothing's yet started to precipitate out. So as long as this is greater, I will have precipitation occur. And that's what it's asking me, at what point will the precipitation start to happen? Okay, so the silver ion is what I'm trying to find out. And they told me that the potassium chromate solution was 0.001 molar. Now, I did not write out the equation for that dissociation, but you've got to think about that in your head. When potassium chromate dissociates, for every mole of potassium chromate, you have 1 mole of chromate ions. So that means the concentration of chromate ions is going to be 0.001 there. And so then when I solve that, I have silver ion concentration. Remember, that's squared, so you'll have to take the square root. You end up with 3 times 10 to the minus 5 molar. So as long as your silver ion concentration is greater than 3 times 10 to the minus 5th molar, you will have precipitation, okay? It will start as soon as this passes that point, all right? And then we'll go ahead and look at part B as well. This time we have, chemist has a solution that is 0.1 molar in both copper nitrate and lead nitrate. Potassium iodide is added to this drop by drop. So again, we're going to ignore any increases in volume, and we want to know which one of these is going to precipitate first. So this is actually almost like working 2 problems at once. So we'll erase this and give ourselves a little bit more space here again. Go ahead and get rid of this too, because you've already seen that. So I'm looking at 2 separate equations and 2 separate KSPs to determine which one is going to precipitate first. So I want to know whether it's going to be copper iodide or lead iodide. So let's look at my equations here. So for copper iodide, Cu plus I minus. Or the other option is lead iodide, lead 2 iodide to be specific, which is going to be lead 2 plus or 2I minus, and both of these are aqueous. Okay, I know that the KSP for the copper iodide is 1.3 times 10 to the minus 12. And there's my KSP expression. I know that it will start to precipitate when the product of the ion concentrations is greater than the KSP. So what do I know about the ions that are in solution? Well, it tells me that it's 0.1 molar in both copper and lead nitrate. So the copper nitrate, I already know that I have 0.10 molar concentration for the copper ions. It's 1-to-1 when that copper nitrate dissolves, and so I'm left with an iodide concentration over here. So when I solve for that, the copper iodide will start to precipitate when my iodide ion concentration is 1.3 times 10 to the minus 11th molar. Okay, so as soon as we hit that point, copper iodide will start to precipitate. Now let's check the lead iodide. The KSP for lead iodide is 9.8 times 10 to the minus 9th. So again, I'm going to write the expression lead 2 plus and I minus quantity squared. Okay. Once again, when the ion product get my tongue untwisted. When the product of the ion concentrations is greater than the KSP, then it will precipitate out. So here's my KSP. What do I know about concentration? Well, the direction or the problem said that the lead nitrate was a 0.10 molar solution, and there's just going to be one lead ion that is produced per mole. So that's going to be 0.10 molar here, and this is going to be I minus here. And so then when I solve that, now I have 3.1 times 10 to the minus, was it a 4? Yeah, times 10 to the minus 4th molar for my I minus concentration. Okay, so what does that tell me? Well, that tells me since this number is much smaller, that means that the copper iodide is going to precipitate out first. I don't have to have a very high iodide concentration for this to precipitate. It's got to be much higher for this one to precipitate out. So that means the copper iodide will precipitate first. Okay. Alrighty, so 3 examples there as far as other ways to use KSP in your calculations. So I'll let you work on those, and then that gets us to the end of Module 6.